Amid the mist-shrouded Alps, a cable car line stretching more than 1.7 kilometers crosses a vertical rise of more than 400 meters between steep mountain slopes. That entire massive journey requires just 2 tower assemblies to remain stable against violent winds sweeping across the valley. This is Weglosen Seebli, the world's first tri-line cable car system. Along the route, 18 bright red cabins continuously leave the stations, carrying up to 1,400 passengers per hour in each direction into the Hoch-Ybrig ski area. They travel at a speed of 6 meters per second, as fast as a track athlete sprinting at full speed, yet maintain that wind-cutting pace above deep voids and cloud-covered mountain slopes. So how did Swiss engineers manage to carry a new generation cable car system across a deep valley with just 2 tower assemblies? Join Mandarin Tech as we step inside the massive Hoch-Ybrig construction site to find out. Located in the canton of Schwyz, Switzerland, Weglosen Seebli is the vital transport link carrying visitors from the valley up to Seebli, the gateway to the Hoch-Ybrig ski area. The new installation was built to replace the cable car line dating back to 1970 after more than half a century of operation. If this connection were to stop, activities across the mountain would immediately be brought to a standstill. Rather than simply replacing the old cable car, Hoch-Ybrig AG chose this location to deploy the world's first tri-line. Carriages directly implemented the system on site. The technology was developed on the platform of the Doppelmayr Group, while SWA was responsible for manufacturing the completely new generation of STELLA cabins specifically for this line. As a result, Weglosen Seebli became a real-world testbed for a new generation of aerial transport, where the stability of a 3-cable system is combined with a more compact, more flexible structure that is better suited to mountain routes with limited construction space. To build the new cable car line, the first challenge did not lie in the middle of the valley, but right at the 2 ends of the route. The new tri-line had to be built directly beside the old Weglosen Seebli system, while the cabins that had served Hoch-Ybrig for more than half a century continued to operate. Every component, therefore, had to be positioned within a precisely calculated space, close enough to make use of the existing corridor while still ensuring the safe operation of the old line. At Weglosen and Seebli, construction began by excavating foundations deep into the mountainside and pouring massive reinforced concrete structures. These foundations would carry the weight of the entire station structure as well as the forces transmitted from the cable system above. Once the concrete reached the required strength, cranes immediately lifted the main steel beams into position. Assembly progressed at a remarkable pace. From Monday to Thursday alone, the station's main load-bearing frame had already taken shape. But at Weglosen, one major obstacle remained. The path of the old cabin passed directly through the space required by the new tri-line structure. Therefore, even though the foundations and most of the steel frame had been completed, the construction team was forced to leave a gap. The beam ends were installed and left ready on both sides, while the final section remained outside the operating corridor. Only after the final journey of the old system was the area completely closed off. The obstructing structures were quickly removed, allowing a crane to lift the missing section of the frame into its exact position and secure the final connections. The gap once reserved for the old cabin disappeared. In a short time, an unfinished station had become a complete gateway, ready to receive the tri-line system. Alongside the construction of the stations, the STELLA cabins also entered their final assembly stage. Starting from the basic frame, technicians installed the panoramic windows, door system, interior ceiling, and seats. Every component had to withstand prolonged vibration, temperature changes, and the forces generated as the cabin passed through the station's guide system. Each cabin weighs more than 1 ton and can carry approximately 1,500 kilograms of payload. The STELLA platform can accommodate up to 20 people, but the version designed for Hoch-Ybrig is configured for 18 passengers, with 12 seats and 6 standing positions. The remaining space is reserved for winter clothing and ski equipment. The cabin uses a modular design, allowing the seats, storage racks, and interior layout to be changed without redesigning the entire cabin body. The entrance is level with the station floor, allowing wheelchairs and strollers to move directly into the cabin. Ski racks are also placed inside to reduce aerodynamic drag while the cabin is moving. Above the cabin is the carriage, the component that supports the entire weight of the vehicle. Two D5000 grips connect to the haul rope, while 8 wheels arranged in 2 rows run along 2 fixed track ropes. This clearly separates the 2 functions. The track ropes carry the load, while the haul rope provides the motion. The distance between the 2 rows of wheels creates a wide support base, helping the cabin remain more stable when exposed to crosswinds on the mountainside. This structure allows Tri-Line to combine high transport capacity with greater stability before the entire system is placed into operation. Once the stations had taken shape, the focus of construction shifted to the steep mountain slopes. No crane could reach these locations, forcing the massive tower assemblies to be installed from the air. All preparation work, including dimensional checks, ladder installation, and marking the bolt holes, was completed at the staging area. Up on the mountainside, the helicopter could hold each load in position for only a matter of minutes. Super Puma flights were concentrated in the early morning, when the air was still denser. Even a slight rise in temperature would immediately reduce rotor lift against the weight of each 3.7-ton steel structure. As the helicopter approached the installation point with its load, the rotor wash blasted dust and debris across the site. Workers could only move in once the steel structure entered the safe control zone, then quickly used guide ropes to rotate the flange into alignment with the base column. Hundreds of high-strength bolt sets, 112 for the first section, 96 for the second, and 84 for the final section, were tightened to turn the separate tubular sections into a single steel spine. The greatest technical challenge lay in the uppermost cable saddle assembly. Instead of resting on a single axis, it had to sit simultaneously on 2 parallel steel columns. The spacing, height, and inclination of the 2 tower tops had to match with near-perfect precision. Any difference between them could prevent the elevated steel assembly from fitting into its mounting points, directly threatening the load distribution of the entire system later on. The track rope system weighs hundreds of tons, far beyond the lifting capacity of a helicopter. Therefore, the construction team had to pull each steel rope across the valley using a sequence of guide ropes that gradually increased in size. The Super Puma opened the way by laying an ultralight pilot rope over the tops of the 2 tower assemblies. This rope then pulled a larger intermediate rope, which was subsequently connected to the end of the main cable. By replacing the ropes step by step, a sufficiently strong connection was gradually established between the 2 stations without having to lift the entire cable reel into the air. At the upper station, the main winch generated a pulling force equivalent to 25 tons to haul the cable up the mountainside. At the opposite end, a Zec braking winch maintained a restraining force of around 16 to 17 tons. One side pulled while the other held back, keeping the cable under controlled tension. Workers continuously monitored the tension and sag to prevent thousands of meters of steel from touching the terrain, rubbing against structures, or twisting as it passed over the tower saddles. Once the 2 track ropes had been secured, the construction team closed the haul rope, which measured 46 millimeters in diameter. The 6 steel strands at both ends were opened up, interwoven over a section tens of meters long, and then tucked back into the core. No welding or metal clamps were required. The tension of the entire line caused the steel strands to tighten around one another. The 2 fixed track ropes and the closed haul rope loop were now ready to put the Tri-Line into operation. Once the haul rope loop had been closed, the station entered the final stage of completing the drive system. The motor, gearbox, drive sheave, and bearing assemblies were connected into a single transmission chain. The drive sheave had to rotate precisely on center, the groove had to grip the rope evenly, and the bearings had to distribute the load uniformly to prevent vibration, rope slippage, or localized wear. The STELLA cabins, each with a capacity of 18 people, were then brought into the lower station, connected to their hangar arms and carriages, and fitted with automatic doors, lighting, communication systems, and control signals. Once on the line, each cabin gripped the haul rope and accelerated to 6 meters per second. When returning to the station, the grip opened and released the cabin from the moving rope. Rows of friction tires then took over, slowing the cabin for passengers to board and exit before accelerating it again so the grip could reconnect with the haul rope at the station exit. Once all 18 cabins had been placed on the system, the tri-line entered its final testing sequence. The service and emergency brakes were calibrated under different load conditions. The cabins were loaded with simulated passenger weight and operated under full load, unbalanced load, power loss, and fault scenarios to test every layer of protection. Sensors at the stations and along the line continued to monitor the motors, brakes, doors, cabin positions, and movement of the cable system. The control system could automatically slow or stop the line when an abnormal condition was detected. Finally, the Swiss Federal Office of Transport reviewed the documentation, witnessed the load tests, and assessed the safety equipment. Only after completing this entire process was the Weglosen Seebli tri-line officially ready to carry passengers. In November 2025, Weglosen Seebli entered a new chapter. The steel structures and cables once scattered across the construction site had now come together as a complete transport system. For visitors, the journey begins only when the doors close and the cabin quietly lifts away from the ground. Behind that smooth movement are thousands of calculations and countless decisions that had to be precise from the very beginning. The project brought tri-line beyond the drawing board, proving that a new technology could mature in demanding terrain and create another option for mountain transport. From here, hard-to-reach regions may be able to increase transport capacity while limiting their impact on the surrounding landscape. If the tri-line Weglosen Seebli opens a new generation of cable transport for Hoch-Ybrig, then in Bernese Oberland, the Steckelberg-Mürren line pushes mountain engineering to the extreme with one of the steepest gradients in the world. In the freezing Swiss Alps, where mountain cliffs rise almost straight up, a massive transportation system hangs suspended in midair, held in place by only a few steel cables stretched across kilometers of open space. With a slope approaching 60 degrees, this is the steepest cable car ever built in the world. It is pulled almost vertically up the rock face. But the most astonishing part lies behind the scenes. On this extreme construction site, workers must suspend themselves thousands of meters above the ground, installing each pulley, each bolt, and each steel cable. A place where even the smallest mistake leaves no second chance. This cable car line is called Steckelberg-Mürren, located in southern Switzerland, one of the most rugged mountain areas in Europe. Stretching over 1.1 kilometers and climbing nearly 800 meters in elevation, the system pushes cable car engineering beyond traditional limits. 2 cabins, each capable of carrying up to 85 passengers, travel along a route with a maximum gradient of 159%, a level so extreme that very few transportation systems anywhere in the world attempt it. What makes this project truly remarkable, however, is not just the numbers or the records it breaks. It is the way engineers build, install, and operate a suspended system in fierce winds, heavy snow and terrain, where even the smallest mistake is not an option. The first step in building this cable car line is the design stage on paper. At this point, experienced engineers must calculate every factor that could affect the system. The steepness of the cliff, the height and position of each tower, extreme wind forces, cabin load, cable tension, and even small vibrations as the cabin moves. This is not a job for ordinary engineers, but for highly seasoned specialists, because even a tiny error on the drawings could make the entire system unsafe to operate. In the end, they chose a 60-degree incline. It is a bold decision, but the only design that truly fits the terrain at the destination. In the final stage, the cable car system enters the testing and commissioning phase. The line is first run without passengers to check cable tension, drive performance, braking response, and system stability under different speeds. Gradually, test loads and empty cabins are added to simulate real operating conditions. Engineers monitor vibrations, wind behavior, and emergency systems to ensure everything performs within design limits. Only after all tests are successfully completed is the cable car officially approved for passenger service. So, you've now gone through the entire process of building a cable car line with me. From the initial design drawings to the moment the system is ready to operate, In reality, this is an extremely complex process, and in this video, I could only cover the main stages of such a massive project. If you notice anything that isn't fully accurate or would like to add more technical insights, feel free to leave a comment below. Thank you for watching, and I'll see you again in the next videos on Mandarin Tech.